Hello and welcome back. This is our second lecture. We will be going over chapters 2.3 and 2.4. We're going to use Venn diagrams to study set operations, and we're going to use these sets to solve problems. Let's jump in. So first I'll talk about what is a Venn diagram and some set operations that we'll need to know. So first, when constructing a Venn diagram, we must always have a universal set denoted U, similar to how we had a universal set in the last lecture. The universal set is the set of all elements under consideration. So our universe that we live in. The set union is defined as the union of two sets A and B is set of all elements that are in A or in B. And then we have some notation. So the U means union. And last time we did learn that the upside down U is intersection. So the intersection is defined as the set of all elements that are in A and in B. So let's do a light example. Let's say our universe is, let's use 1 to 10. So numbers from 1 to 10. Let A equal 2, 3, 4, 5, and let B equal 4, 5, 6, 7, 8. All right. Then for union, A union B is all the elements that are in A or in B in both sets. So we have 2, 3, 4, 5, 6, 7, 8. Because every single one of these elements is in either A or B. So even though, say, the number 8 is not in A, it is in B. So it is in their union. Now with intersection is A and B. So it must be a common element shared by both sets. So A intersect B is going to be only the elements that A and B have in common. And if we look up at the top of this slide, we will see the elements they have in common are only 4 and 5. So union is anything in either of the sets. Intersection is only what they have in common. And remember, if they have no elements in common, if they are disjoint sets, their intersection is empty, which we learned in the last lecture. Okay, let's do an example with two sets. I'm going to draw you a Venn diagram with two sets. Now with Roman numerals, I'm going to label each area. So we'll call this one 1, their intersection 2, 3, and 4. There are 4 areas of this Venn diagram. The part in A but not in B is Roman numeral 1. So these are elements in A but not B. Roman numeral 2 are elements in both A and B. This has a fun name and great notation. It's their intersection. Roman numeral 3 is where we have elements in B, but not in A. And then Roman numeral 4 are elements in U, but not in A or B. All right. So say we wanted to discover which areas make up A union B. Their union. We're going to look at 1, 2, and 3. What about A union B complement? The complement of the union. Well, we did learn last time that a set complement is anything in the universe that is not in the set. So A union B complement is going to be elements in U, but not in A union B, which means elements in U, but not in A or B. So that's going to be Roman numeral 4. So looking at A union B complement, you can see I don't want any elements in A or in B. I want everything else. So it's going to be everything out here in this area. And since the only thing out here in this area is this Roman numeral 4, that's what's in A union B complement. Let's do an example with 3 sets. First, I'm going to draw you the Venn diagram with 3 sets. Next, I'm going to label all of the areas with Roman numerals. All right. Now we'll look at each area and figure out what it means. Roman numeral 1. This represents elements in A, but not B or C. Roman numeral 2 represents elements in A and B, but not C. Roman numeral 3 represents elements in B, but not A or C. Roman numeral 4 represents elements in A and in C, but not in B. Roman numeral 5 are elements in A, B, and C. So all 3 sets intersect at Roman numeral 5, and it is what every set has in common. 6, elements in B and C, but not in A. Seven elements in C, but not A or B. And lastly, 8 elements in U, but not A, B, or C. U is pretty much everything else. Can we use this to find something slightly complicated? For example, let's try to find A intersected with B intersects C complement. First, let's find B intersects C complement. B intersected with C is going to be this area here that I'm shading. This is B intersects C. However, we want the complement of that. So the complement of B intersects C is quite literally everything else that's not in this green shaded area. But I don't just want the complement of B intersects C. I want the complement of B intersects C intersected with A. So what this is saying is everything that is in A, but is also not inside this green shaded area. So let's just start coloring everything in A. Well, I have this piece and this bit and this bit, because they are all inside of the circle that defines my set A. Since this circle here is what defines the boundaries of my set A. So this is going to be everything that is shaded blue. So this is equal to Roman numeral 1, 2, oops, set brackets, and 4. Let's do another one. I'm going to erase my current scribbles and then we will do another example. All right, let's do another weird one, kind of like what we just did. Let's do B union A union C complement. What we're going to do first is find A union C. So we want everything inside of A as well as inside of C. So the green shaded area is A union C. However, we want to union B. We want B to join the complement of A union C. Now the complement of A union C is going to be everything not in the green shaded area. So if I'm going to union everything in B, and all that's left over is this Roman numeral 3. Granted, these other 3 Roman numerals, 2, 5, and 6, are in B. They're in the complement of A union C, and I can't use anything in that green area. So I'm only going to use this 3. And then I'm unioning it with everything else. Well, what else is there? 8. So B union, everything not in the complement, B union, everything not in A and C is going to be 3 and These are De Morgan's laws. For any two sets A and B, A union B complement is equal to A complement intersected with B complement, while A intersect B complement is equal to A complement union B complement. We're going to show that these two things are true using the universal set 1 through 5, A being 1 and 2, and B being 3 and 4. So first, what we will do is find A union B. A union B is everything in A, everything in B. So we have 1, 2, 3, 4. Now the complement of A union B is going to be everything that's in U, our universal set, but not in A or in B. The only number left over in U that doesn't show up in A and B is going to be 5. Oof. So A union B complement is 5. Well, let's see if this works if we also do A complement intersected with B complement. Well, A complement is everything in U, not in A. So that's going to be 3, 4, 5. B complement is going to be 1, 2, and 5, because we don't want the 3 or the 4. Now A complement intersected with B complement is going to be everything in our A complement set in our B complement set. Now the only number that these two sets have in common is 5. So you can see here that our first De Morgan's law does hold up. A union B complement does in fact equal A complement intersected with B complement. Let's try the next one. Well, when we do A intersected with B, A and B don't have anything in common. So it's the empty set. What is the complement of the empty set? Here is a fun logic problem. We want everything in the set U that is not in the empty set. Well, but the empty set doesn't have any elements. So the complement of the empty set is the whole set. Oh, I wrote union and not intersection. Oops. Intersection. Let's see that one more time. Because the empty set has no elements, the complement of the empty set is all of the elements. It is kind of a fun logic problem, huh? Alrighty. So now we need to find the other part of this. So it says A intersect B complement is supposed to be equal to A complement union B complement. Well, let's find out. A complement, actually we found those up here, so I'm just going to use those because we already did that. So from up here, A complement union B complement is, well, A has 3, 4, 5, and B has 1, 2, 5. We want the elements in both sets. So that gives us 1, 2, 3, 4, 5. Now we can see that A intersect B complement is equal to A complement union B complement. So we've done that too. Moving on. Example. Suppose A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and B equals 6, 7, 8, 9, 10, 11, 12. Draw a Venn diagram to find the cardinality of A, B, A intersect B, and A union B. Well, we love drawing Venn diagrams, so this is fabulous. So what is in the intersection? I like to find the intersection first. I see we have a 6 in common, and a 7, and an 8, and a 9, and it looks like nothing else. So 6, 7, 8, 9 are in both sets. That means 6, 7, 8, 9 is in my intersection. Now remember, what's in this region over here is everything in A, but not in B. So that's going to be 1, 2, 3, 4, 5. This area over here is everything in B, but not in A. So that's going to be 10, 11, 12. Now we want to find the cardinality of A, B, A intersect B, and A union B. And I hope y'all remember from the last lecture that we denote that as N of A, N of B. Okay, well, the number of elements in A, we can kind of count them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 elements. Now if we want to count the elements in B, 1, 2, 3, 4, 5, 6, 7. 7 elements in B. Next, we are asked to find the cardinality of A intersect B. A intersect B is going to be the amount of numbers in the intersection. So we have 1, 2, 3, 4. 4 numbers in our intersection of A and B. And finally, the number of elements in the union. So now we need to count all the numbers. They do go from 1 to 12, if you'll happily notice. If you start in A, you can read 1, 2, 3, 4, 5. Intersection is 6, 7, 8, 9, and B is 10, 11, 12. So there are 12 elements since they're numbered 1 to 12, which is convenient for us. Moving on. The cardinality of unions. If N of A represents the cardinal number of a set A, then for any two finite sets A and B, the number of elements in the union, or N of A union B, is equal to N of A plus N of B minus N of A intersect B. Essentially, what this is saying is the number of elements in a union is equal to the number of elements in A plus the number of elements in B minus the number of elements that they have in common. So if we go kind of just right back up here, we could try to use that to find this union and make sure that we get the same answer. So N of A was 9, N of B was 7, N of A intersect B is 4. Okay? So this is going to be equal to, well, 9 plus 7 is 16. And 16 minus 4 is equal to 12. So yes, we got the same answer. And I hope that y'all can see that it's important we subtract the intersection, because if I'm counting all of the elements in A and I'm counting all of the elements in B, the elements right here in the middle get counted twice because they're in both sets. So you have to subtract the intersection to make sure those elements only get counted once. Well, let's go through the example on this slide. A survey of 100 students revealed that 42 are taking math, 51 English, and 12 are taking both. How many students are taking either math or English? So let's let A be students taking math, and B be students taking English. So the number of students taking math, or N of A, is 42. N of B is 51, because that's the number of students taking English. And then N of A intersect B is equal to 12. Because the intersection is the both, right? If you're in both math and English, then you are in both set A and in set B. Therefore, you are in A intersect B. So we have the number of students taking math or English is going to be N of A union B, which is 42 plus 51 minus 12, which is 81. Moving on. All right, let's use this Venn diagram to answer some questions. So let's do how many people own cats or dogs? If we're looking for how many people own cats or dogs, that means we're looking in the circle of cat owners and we're looking in the circle of dog owners. So we're going to add up all of these people. So we have 14, 3, 2, 7, 19, and 4. Anybody in either the cat circle or the dog circle. So I got 49. Next, we are going to do how many people own dogs but not birds. How many people own dogs but not birds? All right, so for this, we're looking in the circle here of people who are dog owners. However, we do not want to consider people who are bird owners. So we do not want anyone in this green circle right here. So that means we're only adding the 19 and the 7. All right, this concludes our second lecture. Thank you so much for tuning in. I hope you have a wonderful rest of your day.